Okay, so now look at the equation 18 and 19 and see that this equation 18 can be solved very simply, because this object EL minus H naught minus epsilon P naught H1 P naught is well defined in the P naught subspace, and it acts on SL, which is basically the P naught subspace. And when I use that, so equation 18 by inverting, I can easily invert equation 18, and this whole thing is in the, this is a P naught subspace equation. So by inverting that, I will get the equation 20, and it is simply just by taking the SL, separating the SL from the right hand side. Now in order to get an equation for RL, because it is a coupled equation, it is a usual strategy for solving a coupled equation. So I have to plug equation 20 in 19, and then I will get the equation 21. So carefully you can do this algebra once by hand, but it is very simple exercise, and I strongly recommend you to do this by hand. So you get this equation 21, which is an entirely equation of RL. Okay, by expressing SL in terms of RL, and I now plug in the SL in the equation 19, I will get an equation entirely of RL, which is the degenerate subspace. The degenerate subspace vector equation, which is what the eigenvector is given by RL. So now write down, so now this is an expansion form, and write equation 21 first order in epsilon without any assumption on the RL. I can simply write down the first order term, and with no trouble I can see immediately that it is simply the equation 22. Now H naught, but we remember that this RL is nothing but a projection of the eigenkate in equation 15, the eigenkate L on the degenerate subspace using Q naught. So it's a vectors which are along the unperturbed eigenkates of the degenerate subspace. So it will, when H naught acts on RL, it will simply give me the EM naught, the degenerate states, or the ED0. So that is also, alternatively I will use the notation ED0 to remind that it is from the degenerate subspace. So equation 22 is entirely defined in the subspace HD, Hilbert space HD, which is subspace of the full problem, of the degenerate subspace of the full problem. And equation 22 is a Q by Q equation. So convince yourself by looking at all the matrix. So for that, the first term will have a additional identity matrix multiplied by identity matrix, a diagonal form, EL minus EM naught. This one is a diagonal form, minus epsilon Q naught H1 Q naught. Okay, so now let me introduce this equation 22 is the first order in epsilon equation. So now we want to, let us say we want to solve that and see what is the first order correction. So to do that, before we do that, we introduce a shorthand notation. So I define something called U, which is nothing but this object Q naught H1 Q naught. So I call it an effective Hamiltonian or perturbation Hamiltonian, which is acting in the d-dimensional or HD subspace. So it is basically nothing but projection of H1 and in the d-dimensional degenerate subspace, and I call it U. And another notation like before is delta L, which is basically the shift in the energy because of introducing the epsilon. So that is nothing but EL minus ED0, which is the degenerate space, multiplied by the identity matrix, which is Q by Q. So in that degenerate subspace. So then equation 22 in this compressed notation will become the equation 25. Delta L minus epsilon U RL equal to 0. Now look or notice that this is basically looks like you can think it as a Schrodinger equation itself, or like some kind of a eigenvalue equation, where the Hamiltonian is epsilon U RL is equal to, on its states are delta L RL. Now the delta L part is already diagonal, and the U can be diagonalized. So this, in this problem, let us say you know the effective Hamiltonian, and let us say you can diagonalize the U very simply. So if you can do that, then you have solved the problem. Basically, once you have, if you can do that very simply, you know exactly the RLs, because if you can diagonalize this problem, you know exactly the RL, you know exactly the delta L, and you have solved the full problem. Or you can and most of the cases you cannot do that. So you have to still take help of the perturbation theory, and you can say that you can apply perturbation theory in this subspace, which is epsilon u RL equal to delta L RL, and then you will find some eigenstates of u. So which is either exact or approximate depending on how you are solving this problem, exactly or perturbatively. So let us see how you proceed with this equation 25. So I just described a strategy, and let us implement that strategy. So how the equation 25 looks when I write it in its full expanded form. So what happens when you solve it? So equation 25, as we mentioned, it is just taking the terms from left hand side to right hand side, and u is q naught h1 q naught, and RL is, as we defined, is q naught L. So when I write it down or expand it in the form of in the 0th order L. So now look at this box on the side. So I want to solve this equation 23 perturbatively, and want to ask the question, what is it at the 0th order? And or 0th order means of the order epsilon. Here it is the smallest order epsilon, which is the first corrected phase. That is not the 0th order. The right way to say it is the first order. So to do that, I expand the delta S as delta L naught plus epsilon delta L1 plus dot dot dot, and L as L naught plus epsilon L1 and dot dot dot. So now my this L here is basically L naught plus epsilon L1 and dot dot dot. So the 0th order is k naught L naught k naught, or the k is belongs to D subspace. And now if I write it in the matrix form, we can see that since there is epsilon on this side, the first order in epsilon equation will contain the delta L1, but the L will contain the L naught because of this fact that this equation has epsilon to begin with. So in this side I can have L, this side I can have L naught, and it will be still to be an order epsilon only if I take the delta L to be epsilon delta L1. So order epsilon, the equation will be equation 26, where U is the matrix, which U matrix is written in this form, where this term H111 implies, or H112 implies these terms of k naught H1 k naught prime, or which is the degenerate subspace eigenvectors. Now in order to get the delta L1 or the first correction, I have to solve this equation. Now this equation solution is just like what we discussed. We get this secular equation which will give me the eigenvectors or eigenvalues. Once we know the eigenvalues, we can plug that back in 26 and solve for the eigenvectors. So that is the usual strategy. So the root of this equation has q solutions. I wrote there is a typo, I wrote it g solution, but it should be q solutions. And this q solution, so the strategy is to substitute these q solutions or delta L1, the first order corrections of the equation or roots of equation 27 into 26, and then solve for k naught L naught, which is the find out the eigenvectors. And once we do that, we know the first order corrected energies and the first order corrected or the right eigenkets which diagonalizes H naught and the degenerate subspace of H1 and smoothly connects them. Now starting from that, we can apply the degenerate perturbation theory as non-degenerate perturbation theory as we know. So solving the equation 26 and 27 as I described, we obtain the first order energy shift delta L1 and the correct 0th order states. Now note that this 0th order states, as we again discuss this again and again, obtained as epsilon goes to 0 are just linear combination of various k naught, and that diagonalize the perturbation H1, whose diagonal elements are given by delta L1 L naught H1 L naught, and as it may look like the exactly same formula which we used before. The same of the first order correction is exactly the same formula, but note these L naughts are not those L naughts, they are like the correct L naughts. Okay, that is the equation 28. Also note that if the degenerate subspace would have been the entire space, like in the first problem, the toy problem we are doing, because the entire problem has the only degenerate subspace describe the entire problem. So this exercise if we do the exercise, that will solve the problem entirely and exactly. Then you don't need to do anything further. But most problem will not be the case. And in most problem, the unperturbed eigenkets will start mixing with the degenerate subspace in higher order term, because we know in higher order perturbation theory, the correction terms engages different states of the unperturbed problem, and that's what will happen in this, and we'll see how to treat this. For example, in first order and higher, you will get for eigenvectors, and second order and higher you get for eigenvalues, because we know when we calculate the same equation of order epsilon allows us to solve it for a certain order of states and one order higher for the eigenvalues. So, as we discussed this already, that equation 28 looks the same expression as non-degenerate perturbation theory, except the bases are not like not the same L naught, they are the correct L naughts. Okay. So, now with that discussion, let us try to further simplify the notation and try to find the solution or exact form of this, which we actually use in finally use in various problems. So, we discussed that the Li naught. So, I introduced this notation Li naught, which is basically the eigenstate of U of the effective Hamiltonian U with eigenvector Ui, and I discussed that this is also the eigenvector of H naught, because that is at the 0th order, it is basically simply the linear combination. So, it is not a corrected state in that sense, but it is the correct state. I mean, there is a little bit of word play, but it is basically, you know what I mean if you understood the previous part. So, that so what this step does, it sets what the unperturbed eigenstate we should choose in the degenerate subspace of the original problem, which is the first issue of the degenerate perturbation theory, that this step solves that. So, now in equation 21, expand the equation 21 in the form in the second order in epsilon square. So, when I do that, I get this equation at the bottom, and this term epsilon p naught h1 p naught, that when I expand it, that will give the higher order terms. So, I do not need that term. So, we get rid of that and rearrange things, and then I will get the equation 28 by writing it down in the form of such that it is an eigenvalue equation of RL state. So, you will get on the left hand side, when you rearrange this, EL RL, and right hand side you will get H naught plus epsilon U plus epsilon square Q naught H1 P naught EL minus H naught inverse P naught H1 RL. Now, notice that I can think or treat this problem as a separate perturbation theory problem, where I take the first two terms and call it a H naught curly, and take the other term, call it a H1 curly, which is because now after all this exercise I know the solution of H naught plus epsilon U. It is basically the, because in this degenerate subspace it is basically a non-degenerate solution, because this epsilon because we have already discussed this epsilon U Li U gives me these eigenvalues Ui, and that is basically a non-degenerate perturbation theory problem after I lifted the degeneracy by going to the right states and calculating the corrected energies. Plus I have some perturbation which is H1, which is of this form, and that is basically now it is the equation 28 or 29 can be thought as a problem of non-degenerate perturbation theory. It is a very simple way to think, because the H naught has now eigenvalue which I call EI1, which is ET0, which comes from the H naught, the original H naught. So, the H naught curly has the eigenvalue ED naught plus epsilon Ui, which is the eigenvalues of U, which are non-degenerate. I mean, we expect that to be non-degenerate. I will tell you what happens if it turns out to be degenerate. And the H1 is simply this. Now, notice I cannot say that this problem, the small parameter here is epsilon, because the epsilon is already inside the H naught curly part. So, let us say I have a small parameter which is lambda, which I set to be 1 at the end, just the way we did before. It is another separate small parameter. And now, since H naught curly has no degeneracies left, we can solve this problem by non-degenerate perturbation theory and find the corrections simply RLN, which are n is the order of the correction. So, the first order is using the formula of which we learned before, is simply RLI1 is this formula in equation 30 when I applied in this context. So, now how does it look like when I write everything explicitly? So, you notice that it has this H1 curly. H1 curly is nothing but this whole thing in equation 29. So, let us write down everything in using the projection operators and everything explicitly. When I write it down, so H1 curly is basically K0 naught, Ki naught, this matrix element is that, and when I plug in the whole form of H1 and expand it, the P naught and all these projection operators, I can write it as epsilon square. So, this term comes from Kj0 H1 P naught. So, P naught is the projection operator, let us say I call it the T naught, and T naught belongs to the subspace of, because P naught, I know that the P naught operates in the subspace, which is an outs HD bar, which is the non-degenerate subspace. So, I get this T naught and I expand this, and clearly the T naught is, this will never blow up, and equation 32 is a well defined equation. So, when I plug that back in the previous formula, I get the first correction, which is this equation 33. So, it is epsilon where sum over all these terms, and denominator you have ui minus ej and ed0 minus et0 and so on. So, the equation 33 is the first correction in the formal setting for a generic problem, when the first order perturbation or when the H1 lifts the degeneracy. Okay. So, to obtain the full, but notice that we just worked out the RL, but there is also a SL, which is the part for the which is the non-degenerate part, which is actually the easier part to handle. So, we worked out the difficult part. Now, we have to also work out the easier part to obtain the full correction in the state up to first order. So, the SL is nothing but now. So, now recall the equation 20. Equation 20 we saw that SL is this form, which is so now let us expand the L, which is the usual expansion which we used before, as L naught plus epsilon L1 and keep the first order correction. So, when I do that, it becomes simply SL1, it becomes simply the equation 34, and up to the first order basically. So, we have to drop this in the first order, we can get rid of this term, and because of the epsilon here I have to keep the 0th order. So, that is why you get the T naught here. So, that is what is your basically the solution or the first order correction in SL1. So, when I add these two, I will get the full first order correction. Now, you might wonder that there is a subtlety of how this is written here, because you might wonder why it is there, what is this epsilon doing there, what is this epsilon doing there if it is an epsilon order correction or first order correction, because it should be epsilon free, but it is actually a way of writing these things. In different books actually write it in different way. So, Sakurai keeps that epsilon, but I think that epsilon, so one should be careful about it, because notice in this term you get this as a epsilon correction or the first order. Now, the way we designed this, way we did this, there is no other small parameter, there is no other small parameter anywhere, there is, so which is our lambda in this case, and when I write it down it comes to be of the form epsilon. But in this case I am expanding it, and this is also the epsilon L1. So, there is actually an epsilon here also. So, the more correct way to write this would be, L equal to L naught plus epsilon, which is put that epsilon in front and in this form. So, in this way or in this way there is an epsilon here also, and then that comes from simply from the fact that this is an epsilon order term, and in this case there is an epsilon which is coming because the epsilon order is same as the first order lambda. So, to be correct one should write a epsilon here and a lambda here. So, if you write that, then it is fully correct equation, but I am setting the lambda to be 1. So, that is why this thing could be written as epsilon plus epsilon, epsilon here and epsilon here. Okay. So, when I do that, then I get this form, which is the entire first order correction, which is epsilon free. and that is you can check from Sakurai, that is the form which you have to, if you want to calculate the first order correction blindly, that is what you should use, first order correction in the state, and so on, plus order epsilon square, which I did not write. Now, do this little exercise, it is guided in Sakurai to show that what is the delta L2 or the second order correction energy. It should turn out to be of this form, but work it out by yourself. Now, here is a little bit of afterwards. So, what we have derived so far is based on the assumption that the degeneracy is lifted at order epsilon, or there is no roots in the secular equation is degenerate. In other words, when I write down this equation, the degenerate or diagonalize the subspace, the degenerate subspace, just a second. So, when I diagonalize this degenerate subspace, it is working on the assumption that there is no further degeneracy left, but that is not guaranteed. There could be a further degeneracy. Then we again basically apply the same program again, and so on and so on, and the formulas will of course get much more cumbersome and complicated. In fact, right now I am working on a research problem which has I have to do a fourth order, go up to fourth order in a many body fermion problem using second quantization language, and that sometimes you have to do, and maybe we can do an exercise to see that if there is still degeneracy in order epsilon, what to do and how to, what is the next corrected formula, next order corrected formula. So, sometimes the degeneracy lifted in first order and sometimes the degeneracy lifted in second order and so on. Okay. So, that is all, and here is the summary which I took from Sakurai, that what is the program of how to do for a general problem. So, the steps are following as we discussed several times. So, first step is identify the degenerate unperturbed eigenkets and construct the perturbation matrix V, which is a Q by Q matrix in our language. In Sakurai's language, G by G, if the degeneracy is G4. And diagonalize the perturbation matrix by solving the usual appropriate secular equation. Identify the root of the secular equation of the first order energy shift, and the base case that diagonalize the V matrix are correct zeroth order case for the perturbed case approaching the limit lambda going to 0 or our case epsilon going to 0. And for higher orders, use the formula of the corresponding simply non-degenerate perturbation theory. So, that is it. So, basically we exclude the all contribution for the unperturbed cases in the degenerate subspace, because now in this way of we have already working in the subspace where basically we are solving the problem in two steps. First step is to remove the degeneracy, get the correct states of the original H0 problem, and second step, once you remove the degeneracy, you just use the degenerate perturbation, non-degenerate perturbation. So, that is the program, and that is all.